Hi, I want to introduce 1.1 Euclidean space. Um, so first, I want to talk about the definition of three-dimensional Euclidean space. So, from the textbook, three-dimensional Euclidean space, so you can just imagine a diagram like this, and this is three-dimensional. So each point in this space have have its uh have can be imagined can be stated as a triple. So this is a point. Point is just element of this space. 3D space. So you can we can say Euclidean space is a set called R to the power 3 and consists of points, which is a which is a triples, which are triple. So based on this, we can see that um, a Euclidean space is a set and with points. But when we call it a space, it should have some uh, operations with the set. So Euclidean space have two operations. The first is sum. The sum is element on the space have a sum, which means two elements can be added up together. So if point one belongs to R3, Euclidean space, and point two also belongs to R3, they can be added up together and be a point P. So the operation rule is like if point one can be written as x1, y1, z1, point two, x2, y2, z2. We know if x1, x2, and y1, y2, z1, z2 all belongs to R, a real number, because we know what a real number is. So we can define operation. We can base on the operation of real number to define the operation on a three-dimensional Euclidean space. So point one plus point two is just the uh, sum of each coordinate. So it will be x1 plus x2, y1 plus y2, z1 plus z2. So each of these are just a sum of from real number. So because we know what we real number operation on real number, so we can know the operation of sum in this way by in the Euclidean space. So this is operation one. Then we also need to have another operation, just like a linear algebra. A linear algebra, we do not define a product of 2 points. We want to define a scalar multiplication. So we need to have to scalar. A scalar will be a real number, and by the scalar multiplication, we want a scalar time a point. So if point have x1, xyz as a 3 triple, the scalar will be alpha times each coordinate. So this will be the scalar multiplication. And because we have all operations, we need also have a additional property, which is the origin. So this is trivial. So the origin is just 0 at this point. So next, I want to talk about what is the natural coordinate function. Definition 2. As you can see, we can have a point like this or anywhere in the 3-dimensional space. And we can have a different representation of this point based on what you want. You can represent it in x, y, z coordinate. You can also use another way because we know from linear algebra, as long as we have 3 vector, which are independent, linear independent, we can represent any vector form in the space formed by those bases. So so based on this fact, we can say what is a natural way we can what is the natural way people can identify a point. The natural way is we have orthogonal bases, which means they are pairly orthogonal, so pairly parentheses. So like this. In 3-dimensional Euclidean space, it's just x, y, z coordinate, and they are pairwise orthogonal. So the natural way, if we have a function called x, a function is a relation between two sets. So our domain should be Euclidean space. And from a point from Euclidean space and to another triple, they can be they should be both in the Euclidean space, but different triple. Even though they are different triple, they can represent the same point. So a natural coordinate function is just if we have a point. Actually, we can. It's a better way to write it this way. So if a point in R3, we can use this function to get a triple. actually. So it should be like this. And if P can equals become, so this x is just a natural coordinate function. And the last definition in this section is differentiable. So in the definition, we say a function is a differentiable function f is different is R3 is differentiable if all partial derivative exist and continuous. We can release some condition on this definition if we want. Because if we have some knowledge about topology, we know R3 is a open set and a closed set. So this will be talked about later. So we can think this is an open set. So differentiability can be defined not on a whole space. We can maybe define it on just an open set, open subset maybe. Open subset in our space. So open subset means for if we have an open ball, sorry, we should draw like this way. If we have open set, in each point in the open set, we can have another open set entirely in the larger set. So the larger set is called open set, and this is we can if we as we learn from the ones calculus 1, this is just a neighborhood. So for each set in for if we have an open set, each point in the open set we can find uh, uh, a desired neighborhood which contained in the larger set. So if we understand like this way, the differentiability can be better defined because we can have a loser condition. So this can be generalized more easily. And these three definitions is basically what 1.1 talked about. So in the future, we will learn some details about this. Yes, thank you for listening to my presentation.